Alright, what's up, gang? It's your boy. It's at home Macomb. How you doing? I'm here with the review for our second test here. Going to be going through it and showing you guys all of the tings. Okay, so this first question is an ENH. It's for the easy, normal, and the hard. Most of the conceptual questions are shared by all three versions of the test. It's a good idea to, know what's going on. Okay, so the first question is be able to describe what two things are needed to represent a vector. The two things needed to represent a vector, as we learned from Despicable Me, are direction and magnitude. If you have a vector, we represent it as an arrow. It has a direction, which we represent as some angle, and it has a magnitude, which we represent as some value. So this vector, let's say, is, it's a speed. Let's say it's 50 miles per hour, and it's 30 degrees south, that's not south, Asa, north of east. Then north of east is the direction, or rather 30 degrees north of east is the direction, and then 50 miles per hour is the magnitude. So those are the two ways we describe a vector. We need what direction it's pointing, we need how long it is. The magnitude is represented by the length. It's this number here. So it's the amount of the vector, the length of the line, if you think about it like that. Okay, be able to describe the difference between a vector and a scalar measurement. A vector has a direction. A scalar does not have a direction. The easiest way to tell the difference between a vector and a scalar is, I should move this down a little bit, shouldn't I? It's just like, yeah. Move this around a little bit too. There we go. That's better. A vector has a direction involved, and the scalar does not. So a good way to test for this is to add the word north to the end of a measurement and see if it makes any sense. So for instance, if I say 50 miles per hour north, that makes sense. If I say 50 kilograms north, that does not make sense, right? So vectors are things like, actually here, let's just get a piece of notebook paper. I got pieces of notebook paper now, so I don't have to do my my calculations on dominance plates anymore. So like a vector and a scalar. Vectors are things like velocity, displacement, force, acceleration, velocity, displacement, force, acceleration. Those are the ones that come to mind. Scalars are things like mass and time and energy and temperature and concentration in chemistry, right? So all of these things have no direction. Direction doesn't make sense to put with any of these, but vectors do have direction. That's the difference between a vector and a scalar. So if it makes sense for it to be going in a way, in other words, if you care about the direction that something points, it's a vector. If you don't /can, it's a scalar. ENH, the next one, to be able to define what a projectile is and explain why their path looks the way that it does. That's pretty easy. Projectile, the definition of a projectile is object accelerating from only gravity. An object that accelerates from gravity and only from gravity is a projectile. So no force is acting on it except for gravity. Air resistance as well acts on projectiles, but for now we're ignoring that. Basically, when the only source of acceleration on the object is gravity, that makes it a projectile. Why does their path look the way that it does? I should have made more space for this, sorry. Their path looks the way that it does. They follow curved paths because gravity's acceleration points down. So projectiles curve down like this. Because gravity points straight down, this curve here is showing acceleration. So they curve downwards because they are accelerating, and because the acceleration points straight down because of gravity. Gravity only points straight down. So that's why projectiles curve downwards, is because they're accelerating only in the y direction because of gravity. Gravity curves down. Curve equals acceleration. So something like that for this question. And then the last one, be able to explain the relationship between objects' hang time and total time in air. I made a mistake on this. Hang time and total time in air mean the same thing. I was a little bit sleepy when I wrote this question. Hang time and total time in air mean exactly the same thing. So that's not exactly what that means. What I meant to say was explain the difference between an object's hang time and time to the top of the arc. So here, where v equals 0, right? And the answer, of course, is that the time to the top equals exactly 1/2 of the hang time. The reason for this, of course, is because the gravity on this is acting the same the whole way through. Right? So gravity here and here and here and here and here are all the same. In other words, the same amount of time, the same amount of space that it has to slow down, it also has that same space to speed up during. So what that means is that the initial velocity on this side and the final velocity as it hits the ground are going to be the same with opposite directions. So if this is +5, this is -5 here. And that also means that the time it takes to get up to the top is exactly half the total time it's been in the air, assuming it lands on the same elevation that it starts at. So if we're landing on level ground, the time up and the time down is the same because we have the same distance over which to accelerate. If you think about our kinematic equations, you have an acceleration over some distance. If the acceleration is constant, which from gravity it is, the amount of time it'll take to slow down that much will also be equal to the amount of time it takes to speed up that much. So hopefully that makes sense, because gravity is the same all the way through. Or is constant, rather, in other words. Alright, so that's it for the conceptual stuff, not so bad. On to the vectors. So let's find the x and y components of each of the following vectors. This is pretty easy. To find the x and y components of something, of course, all you gotta do is take the sine and the cosine of the angle. In this case, it's 24 degrees. Take the sine and the cosine of this angle. In this case, it's 71 degrees. Take the sine and the cosine of this angle. In this case, it's 41 degrees. Then you multiply it by the magnitude of the vector, the length. So that's, oh geez, I need to move my camera so it's easier to see this. That's better. Sorry. My setup here is still a little bit jank. I hope you forgive me. So we take sine and cosine of the angle. You're going to put it in your calculator like this. Make sure to close the parentheses so you don't accidentally multiply something you're not supposed to. Multiply that by the length of the vector, which in this case is 15. And then you figure out, using my classic method of the Leesburg, Ohio method, where you say, touch your cosine in Leesburg, Ohio. The side that touches gets cosine. So here, the x side is touching the line. That's our x component. That's our y component. Here, the side that's touching the angle gets the x, or gets the cosine rather, so that's the x in this case. And then here, 41 degrees is touching this line and not touching this line, so we get x as cosine again. So in all three of these cases, our cosine gives us the x component. So then we go sine 24 and cosine 24 times 15. My good friend Mr. Calculator will tell me what that is. Make sure your calculator's in degrees for this, by the way. So that's sine of 24 degrees times 15. I get about 6.1. Cosine 24 times 15 is 13.7. Here's sine and cosine of the angle times 33. So that's sine of 71 degrees times 33, boop, is 31.2. Here we have cosine of 71 degrees times 33. Excuse me. 10.7. And then over here, 41 times 136. 41 times 136. Sine of 41 degrees times 136 equals 89.2. And then cosine of 41 times 36 is going to give us 136. Boop. 102.6. So this is 89.2, this is 102.6, this is 31.2, this is, 10.7, and then the x component here is 13.7, this is 6.1. Did I switch these two? Yeah, I did. Sorry. Oh no, I'm fine, never mind. So, there we go, that's how we solved this part, pretty easy. So if you want to split something into x and y components, in other words, if you have just the magnitude and a direction of a vector, take the sine and the cosine, multiply of the angle, multiply that by the length of the vector, that'll give you your two sides, figure out which one is which by the side that touches the angle. The adjacent side always gets cosine. Alright, easy mode. Let's move on to the next one. So this one here asks us to find the length of these vectors from their components. So here we're going in reverse. We have two sides and we want to find the third side. So here's how we do this. Oh geez, my font on this is really small. Let's see if I can swoosh right in here. It's a little annoying. We'll be okay though. Okay, so we want to find the length of these vectors from their components. So we're trying to find the length of C from these two sides. We're trying to find the length of C over here from these two sides. So how we're going to do this is using Pythagorean theorem. If you have two sides of a right triangle, you can find the third side by doing the Pythagorean theorem, which is a squared plus b squared equals c squared. C squared is your hypotenuse. In other words, it's your whole vector, right? So it's going to be this side and this side, our c's there. A and b are either of your two sides. The order of them does not matter. So you could call this A, you could call this B, or you could switch that. It doesn't matter at all. I'm going to call this side A and this side B over here. So we're going to do a squared plus b squared equals c squared. We have A is 21 squared plus b is 34 squared equals c squared. Over here we have A is 73 squared plus 88 squared equals c squared. Now it's just algebra. So this is pretty easy. 21 squared, oh come on, 21 squared is 441 plus 34 squared oh, you stop it, is 1,156 equals c squared. So then we go 1,156 plus 441, boop, 1,597 equals c squared. Square root both sides, and we can get c equals, I'm going to round to one decimal place, 40, it's 39.96, so I'm just going to call that 40 meters. Alright, over here, 73 squared plus 88 squared. 73 squared is going to be, oh, you stop that right now. McComb struggles with his calculator, the game. 5,329 plus 88 squared is going to give me 7,744 equals c squared. That plus 5,329 gives me 13,000, oh geez, my camera's out of the way, sorry. 13,073 equals c squared. Square root both sides of this. It's going to give us 114.3. A little trick for this too, and that's in meters per second, because these are in meters per second. The unit you can get from whatever these are. A quick trick for this too, by the way, is that your C side, your hypotenuse, will always be bigger than either of your other two sides. Right? By definition, this must be the longest side of a right triangle. So, what that means is that you can double check really quick, just eyeball this and be like, okay, 40 is higher than both 34 and 21. 114 is higher than both 73 and 88. That's pretty good. That's a good sign that you did something right. Alright, let's back up a little bit again. I'm sorry, my camera situation's a little bit rough over here. Okay, so find the angle Q of each of the vectors in the previous question. I named them Q because my keyboard didn't have theta on it. So now we want to find this angle Q and this angle Q. And the way we do this is really super easy. We can do an inverse trig function. On your calculator, you get this by doing second sine or second cosine or second tangent. All of them will give you the same thing as long as you have all three of the sides. You can do sine to the negative first of the opposite side over the hypotenuse side. In other words, the far side versus the vector. For cosine, you could do it adjacent over hypotenuse or close side over the vector. And for tangent, you can go tangent to the negative first of far side over close side. O over A, opposite over adjacent. If you want to get this right every single time, the easiest way, I think, is do tangent to the negative first of the far over the close side. Or in other words, of opposite over adjacent. So we can do that really quick right here. Tangent to the negative first of this angle. The far side is 34. The close side is 21. For this one, it's tangent. The far side is 73. The close side is 88. So with those two things, we can get our two angles. Now, my phone calculator, which is the calculator I'm using, is not good at doing this, so I'm going to have to go to Google. Calculator.com. Make sure your calculator's in degrees. The calculator on Google defaults to radians because it hates me. So we're going to go ahead and do arctangent of 34 over 21. Make sure it's all in your parentheses like I have it written down here. I get 58.29 degrees. I'm going to call that 58.3 for the first one. And for my second one, we're going to do second tangent, inverse tangent, arctangent, if you can call it that, of 73 divided by 88. Oh my god, I hate you so much. Sorry, my keyboard's being annoying. There we go. And we get Q equals 39.7 degrees. So that's how we get our 2 degrees. Pretty cool. And if this question asked us to find the other angle too, if it wanted us to find this angle as well, all we'd have to do is subtract these from 90, right? So 58.3, 90 minus that is going to be 31.7. So this is 58.3. This is 31.7. And then over here, 39.7 is 50.3. So that's 39.7 and 50.3. Add up to those two sides. Again, 90 degrees, we know that these two angles must equal 90 because this right angle is 90. So that's how you do it. Pretty easy. Not so bad. Alright, next up. Find a resultant vector, magnitude, and angle that the following set of vector components make when added together. Okay, so if I give you a bunch of vector components, we will add them together and we want to find the vector that they make. So the first things first, we got to add all the x's and we got to add all the y's. So we're going to get x total and y total here. X total. We have 216 plus negative 400 plus 612 plus negative 365. I'm just going to jam that into my calculator. 216 minus 400 is negative 184, plus positive 612 is positive 428, minus 365 is positive 63. Our y total is going to be negative 90, plus positive 187 is 97, plus positive 211 is 308, minus 743. We get negative 435. So these are our two components of our vector. Our x component is 63, and our y component is negative 435. So now, if we want to find, I'm going to get my Dora the Explorer on right here really quick. If we want to find the angle on the side of this, what are we going to do? That's right, we're going to use the Pythagorean theorem again. So we have the two sides. Again, if you have two sides of a right triangle, you know the third by doing the Pythagorean theorem. So this side we're going to call C, and we can call this A, we can call this B, and we can do good old A squared plus B squared equals C squared. When you're doing this, go ahead and just ignore your negative numbers. In geometry, the negative shows us that it's going down instead of up, which is relevant. That's important for determining the direction of this. But truly, in geometry, the side lengths don't have, you can't have a negative side length. It just shows us direction here. So you can treat these like they're positive numbers after that point, outside of the purposes of like determining direction. So we get 63 squared plus 435 squared equals C squared. Oh, calculator friend, please help me out. Okay. 63 squared is 3,969. Plus 435 squared is going to be a big number. 189,225 equals C squared. Add that to 3,969. We get 193,194 equals C squared. Square root both sides of this. We get C equals 439.5. That's our length. So this is 439.5. And then to find this angle, we can do inverse tangent again. I'm going to do tangent to the negative first of the far side over the close side. The far side is 435. The close side is 63. So we're going to go back to Google. Second tangent of 435 divided by 63. Baba Booey. 81.75 degrees. So this is about 82 degrees. Cool. So that's how we do that one. Again, this is pretty easy. This is on the normal. There's a question that's very, like, basically this exact question that's on the normal and hard version of the test. Effectively, all you got to do is you add up your components. That gives you the components of the triangle you make. You make a right triangle out of the x and the y component, and then you use Pythagorean theorem to solve for the side and the inverse tangent to solve for the angle, which is pretty cool. All right. Next up is a question that's only on the hard version. This is effectively the same as this question, only now, notice instead of giving you components, I gave you vectors that you have to break into components. Right? This is just like the last one. This is a question that basically appears on the exam almost exactly like this, but with different numbers. This is basically a parallel problem. So I feel like I'm going to need a paper for this. So we have vector h, vector I, vector j, and vector k. And what we're going to do is we're going to break these into their components. So we solve exactly the same way as we solved this one. We're adding vectors together. The only difference is that I did not give them to you in the form of components. These are in the form of actual vectors that we have to break into components. So h, first things first, is 69 degrees south of east, or 68 degrees south of east. East is this way, south is this way. So south of east means 68 degrees this way. So this is our vector h. It's 419. And we're going to find hx and hy. I'm going to do standard array for my signs. So we're going to do up and down. So north and east being positive, and then down being south as negative, and west being to the right, left as negative. So like this will be our signs here. We have hx and hy. That's negative, that's positive, because that's going to the right and down, respectively. Let's go ahead and find hx and hy. So again, we have a vector length, we have an angle. We can find the two components of this by using sine and cosine. So we're going to do sine of 68 degrees. So that's, oh, my cat is meowing so sad. We're going to do sine of 68 degrees times 419, and we're going to do cosine of 68 degrees times 419. The cosine, it touches the x, so cosine is going to the x, the sine is going to the y. So sine times 419 gives us 300, I'm going to round to one decimal point, 388.5 for our y component, and then our x component is going to be cosine of 68 degrees, cosine of 68 degrees times 419, 157. We'll round that too, so we'll call this positive 157. And that's negative 388 because it's going down. Okay, so that's how we get our first two components. We have hx and hy now. Next up, let's look at vector I. I is going south of west, which means that west is here, south is this way, so south of west is like this. So this is 22 degrees, and this is 281 meters, equals I. Here's I sub x, here's I sub y. This is going to the left, so it's negative. This is going down, so it's negative. So we can go left to the left and down, that's negative and negative. So we'll just make sure to put a minus sign in front of these when we're done. All right, 22 degrees. We're going to do cosine and sine of the angle of 22 degrees. Multiply it by the length, which is 281. All right, cosine 22 times 281 is 260. Oh, the x side touches our cosine again, so that's going to be our x component. That's going to be our y. So that's going to be 260.5. So this is negative 260.5. And then our y component is going to be sine of 22 times 281 is 105.3. Negative 105.3 for IY. Excellent. Next, we have vector 561 meters straight north. That's really easy, actually. So when we have a vector that is going straight in a cardinal direction, it is all on the y-axis. Oh, sorry, I'll move this over here again. It is all on the y-axis and not at all on the x-axis. So what that means is that J's x component is going to be positive, or going to be 0, and J's y component is going to be positive 561. Because it's not going in an angle. We don't actually need to. Do any trick with it. Because it's moving straight north, it's all on the y-axis and not at all on the x-axis. If we had a straight line going east, south, or west, also, we would do exactly the same thing. So positive, it's going positive on the y-axis only. Oopsie, north. So it's positive 561 as our y component and 0 as our x component. Great. So vector k is going to be 273 meters, 422 degrees east of north. This is obviously switched. I meant for these two to be different. So it's 422 meters, 73 degrees east of north. My apologies. That's what it's supposed to say. So east of north is this way. This is 73 degrees. This is 422 meters. It's going up and to the right, so our x and our y component are both positive. Oh, oopsie, sorry. Pardon me, sorry. We need to enclose the angle in the side. So this is our y direction, this is our x direction, because this is 73 degrees. If I did this way, then this would be 17, because it's 90 minus this. These two add up to 90, right? So my bad. You have to enclose it like this. Sorry. Okay, so we are going to do sine and cosine again of our angle, which is 73 degrees. The touching side gets cosine, which is y this time, right? The y side touches. And then it's going to be that times 422. Like I said, it's going up and to the right, so they're both positive. We can get our components really quick from this. So we take the sine of 73 degrees times 422, 403.6 is our x component. We take the cosine of 73 degrees. That's not what I wanted to do. Mr. Calculator, cosine of 73 degrees times 422 and 123.4. Right? Hold on a minute. I'm having a small moment. I need to just make sure that I did that correctly. Yeah, 123.4. Cool. So here are our components. What we're going to do now is I'm going to move this over to another piece of paper, and we're just going to copy this down really quick so that we can do the rest of the work on this. Okay, so we have our, just one second, we have hx is positive 157, hy is negative 388.5, excuse me. We have ix over here, which is negative 260.5. We have iy, which is negative 105.3. We have jx, which is 0. We have jy, which is positive 561. And then we have kx, which is 403.6. And we have ky, which is 123.4. Okay, so move over to my paper that I have here. So all I did was write down the components that we just found. We're going to go ahead and add these together to get x total and y total. And then we're going to do some trick with that really quick, just like last time. So that now this, from this point forward, this question is basically exactly the same as the last one was. So 157 plus minus 260.5. So that's kx, hx plus ix minus 0. Plus 403.6 is 300.1. So our x component is 300.1, and then our y component is going to be negative 388.5. minus 105.3 plus 561 plus 123.4. And we get 190.6 for that. So positive 300 going this way is our x component, and positive 190.6 is our y component going this way. And then we want to find this angle and this magnitude. So the magnitude is easy. All we got to do is Pythagorean theorem. A squared plus b squared equals c squared. So that's going to be 300.1 squared plus 190.6 squared equals c squared. Oh, geez. Baba Booey. 36,328.4. Oh, geez. Oh, crap. I'm dropping my calculator. Oh, God. It's all going to heck. Sorry. Okay. So this is 36,328.4 equals c squared plus 300.1 squared. It's going to be a little bit over 90,000, excuse me. That's going to be 90,060.01. Or 90,060, I guess. We'll not round that on. Alright, so let's go ahead and add these two together. This plus 36,328.4. Boop. We get 126,388.4 equals c squared. Square root both sides of this, and we get our final answer, which is a lovely 355.5 meters. So this side is 355.5. Now we want to find this angle. All we got to do is inverse tangent really quick. It's tangent to the negative first of the far side over the close side. That's going to be 190.6 over 300.1. Back to Google. Please don't screw me, Google. Put my calculator in degrees so that you don't ruin my life. That's one inverse tangent, arctangent of 190.6 divided by 300.1, close parentheses, we get 32.4 degrees. So, there we go. And that is the conceptual and the vector problems. I'm going to make the projectile problems into a separate video. But yeah, good luck, guys. I hope that you found this helpful. And I'll see you next time.